Okay, good morning. Any question from last week? Any question? Okay. So I think let me just review for a moment for this one. Okay. So what you need to be careful is how the curve rotates. Okay. So rotations about x-axis, about y-axis. So rotation about x-axis, you need to imagine where the circle will be and what is the radius. Okay? First write this down. Okay? Or if you have these rotations on y-axis, okay? So this will be your circle and x will be your radius, and this will be the surface area, okay, for the when you rotate. Okay? And then we need to define our ds, okay, the arc length, the length that is supposed to be in the sides, right? And it depends, okay? If we are having trouble or maybe having obvious equations, for example, if the ds is okay, maybe it's easier to use x. For example, if this left side, okay, if the ds is easier to be computed by dx, then you need to define y in x. Okay? If the ds already in dy, then you can just write this y. Okay? And the same thing for this right side. We will do the same thing. If the ds already easy for you to solve in x, then you could just write x. But if it is a dy, then you need to define x in dy, in y. Okay? Now maybe I will give you another idea, okay, before we move to chapter 10 for today. Maybe just a few moments. So let's see these two questions here. Okay, it is called the finite infinite situation. Okay? So if you see the first one, the number 33, you will see a curve. Okay, 1 over x. Okay, well, it's called the Gabriel formula. You will see y, okay, if you look up the solutions later. So for starter, this is y over x, okay, and it's rotated, okay, rotating the curve, okay, is 1 over x about x-axis. So this will be the rotations, okay, and then we are going to observe from x greater or equal 1, which means this is our starting point. And we are going to, well, it is just to, well, the question is, we need to show or we need to prove the surface area. Okay? It says it will be infinite. Okay? Although the volume is finite. It's interesting. So we'll see when you calculate, you can try compute the volume first. Okay? Compute the volume. Okay? Compute the volume. I think you still remember how, or no? Or no? Okay, volume is just taking the radius, okay, pi r squared, right? Okay. And then compare with the surface area. Okay. Rotate about x. Okay. So maybe you can try first. How to solve this is actually at the process you are going to compare the so you need to use some comparison method. If you remember last calculus, in calculus 1, you have a comparison method to show whether the integration is converged or diverged, right? If you remember how. Okay. So we can start with the, I think let me put here. Let me make it a little bit small. Okay, we could start with, if you remember, s is equal. Let me write 2 pi outside of the integrations. It says that from 1 to, not sure how much, but it says going to be infinite. And then the radius is y, right? And then the s, right? And we know that we have y equal 1 over x. Well, you could try both. Okay? You could try 1 over x, or you could try x equal 1 over y. But I will just state with the y equal 1 over x. Okay? So I will convert all the ds into dx. Okay? So first is I'm going to take my first derivative. This will be 1 over x squared minus, right? And then take the squared, and then plus 1, right? Plus 1. So this will be equal to 1 plus 1 over x to the power of 4. So I will take this with the square root inside the ds. So s this is 1 over x. I will change to all into dx. And then 1 plus 1 over x with power of 4. Okay? And then dx. Okay, now let's simplify this square root. This will be x power of 4, x power of 4 plus 1 dx. Okay, I will factor out the x power of 4 for the denominator. So this will be square root x power of 4, and then x power of 4 becomes x squared multiplied by x is x cubed, right? Okay. Okay, now how to solve this? Or rather, we could go back to the question. What's the question asked? It's just to prove whether it's infinite, right? So, do we need to solve this? We need just to prove, right? Okay. So, what's better idea or better solutions to prove this? I already mentioned earlier what you need to do. Yeah, comparing, right? Comparing with something. So remember, we have 1, we have infinite. So it's supposed to be you remember chapter 7, right? Chapter 7, we have the integration. We say the improper integral, right? One way to prove the improper integral is to take some comparison, right? So if you remember, if we take, let's say 1 infinite, 1 over x, and then we have 1 infinite, 1 over x squared, right? This will be diverge, right? This will be converge, right? And remember, to solve this, you need to use the limit, right? Use the limit. We could take the limit as, let's say, t goes infinity. So we have 1 t, 1 over x dx. And we can try to solve this first. And you will see that 1 over x become the ln, right? Become ln, and you will see that it will prove that it will be diverged for this one. But this one will be converged, okay, if you remember. Okay? Because at the process, you will see the 1 over the variables, which is 1 over infinite is 0, right? In this process, okay? I hope you still remember, okay? Okay, now the same thing with this question here, this one. Okay. So suppose that suppose if we see the square root, okay, we have x with power of 4 plus 1. Of course, this will be greater than x with power of 4, like that, right? Okay, pretty much makes sense, right? Pretty much makes sense. And this square root of x with power of 4 is x squared, okay? So this is true for x positive, right? Now, if we take the let's say we have comparison between these two. So we have this. This is the questions, right? This is the question. And this will be greater than this. X squared over x cubed. Okay? Which means that this can be written as 1 over x dx. Okay? Now, this is diverge. Okay? Which means that this will be diverged. Okay? This will be diverged. Which means that the surface area is actually diverged, or you could say it's going to be infinite. Okay? You could try to find the volume, and you will see the volume is finite. So this is a little bit weird phenomenon. So the volume is finite, but the surface area is infinity. That's why it's called one phenomenon called the Gabriel horn. Okay. You could check on other source as well. It's interesting actually. Okay. So there will be a case where you find the surface area is infinite, but the volume is finite. So you could compute the volume and find the numbers, but you couldn't find the number for this surface area. Okay. So we could say at the end, the conclusions, that S this will be diverge. So the area S is infinite. Or let me write completely by comparison method. remember, in comparison method, what you need to be aware of is if you find this converge, then this can be both, right? Can be both. It's not always necessary to be also converged. But if this is diverged, the one that is bigger is obviously should be diverged also. Okay. Okay. So that's the just one point that I need to add. There is a case where you could find the volume, so you can compute the volume, you can find the numbers, but the surface area is infinite. Okay. There's one case. We call it Gabriel horn. Okay, for number 34, I would like you to try by yourself. Maybe not now, maybe just at home. You can try to write the question first. The question is just the curve is y equal e with power of negative x. X is from 0 to all positive. Okay. Rotate on x-axis. Okay. And the same idea, find the resulting surface. So if the questions didn't give you any range precisely, it means that you are going to compute from 0 to infinity. Okay. So you need to, when you compute the integral, you need to use some theory from improper integral, which means you are going to use the limit. Just a little bit review. Okay. I hope you can try at home. This one, okay, number 34. And perhaps in the solutions, you are going to, I think my suggestion is maybe going for some substitutions that are inside in the integration. But you can try first. You can try first. Okay. Okay, I think, okay, we can move on and let's try at home. Okay, number 34. Okay, now the next is we are going to move to chapter 10. So chapter 10 is we call the parametric equations and polar coordinates. Okay. Okay, now I have this curve. This is the coordinate x, y. But I can make this xy into another function, and we introduce another variable we call the variable t, a variable t. Okay. So x is f of t, y is g of t. Okay. The easy way to visualize Okay, this is my only suggestions. Imagine that this is like a positions, okay? Like x is positioned in the horizontal, y is positioned in vertical. Imagine that. Okay? And imagine the t is time. Okay? It's like in physics, you remember how to compute the velocity, accelerations, and so on, right? And you remember if you place maybe some part of some component that you want to know how the component moves. You could imagine, like, for example, from here at this x, y positions, maybe t is 0, maybe this is t is 1, t is 2, and then it's like it's moving, okay? Imagine like that. Okay, I think that's one way to imagine. Okay. So in parametric, of course, the vertical line test that you have before, this will be fail, right? This will be fail in parametric. So this is impossible to describe the curve, okay, with the functions. So if we write y is f of x, this is not ideal. It's not possible, right? Because when you draw this line, it's crossing all these 3 points, right? Or here, it's failing the vertical line test. So it's not y equal f of x. Okay? So this is a different world, okay? Not our usual functions. Okay? The functions become each x and y is f of t and g of t. Okay? So we are going to have, we call this t as parameter, and this is called parametric equations. So each value of t, they will determine both x and y. Okay? And the curve we call parametric curve. Okay? Well, it's not necessarily need to be written as t. Okay? It can be any variable, but this is how we usually define, okay, with t. Okay? So my tips is, imagine x, y is position and t is time. But you will see that the t itself, it can be negative as well. So because t not necessarily to be defined as time. This is just to help you to visualize, I think it's similar with the thing with physics. If you remember how the object moves, find the velocity and so on, right? Find the positions. Okay. Now also, another thing on the parametric, okay, because we define the variable in t, so whenever we start with any t and then we vary the t, for example, t 0, 1, 2, 3, to know which one is which, we need to take the arrow, which means we start from maybe from here, and it goes like it's moving, and maybe here. Okay, so there's a direction. There's a direction. So direction has a direction. Okay, so there will be an arrow indicating the directions, okay, on the curve, along the curve. Some curve probably maybe there are, for example, if you remember the trigonometric curve, it goes like this way, right? Oscillated. So if you compile the trigonometric into the parametric, maybe it's like it's moving like your physics. Yeah, like a pendulum. It goes left, right, left, right. But if you see how it's oscillates, it's like in trigonometric, right? So if we move into the parametric, it's like maybe it's going left, right, okay? I think we will see in another example. For now, okay, if you have a textbooks, you can just read for a few page in the early page in the textbook. I just took the same example. Now, if we need to sketch, okay, let's say we have this x, okay, and then we have this y. And then from those equations, okay, we're going to have some variation for x, y for each time, or t, let's say just t, from -2 to 4. Okay. Y -2, you will see in the graph later. So -2, we put on into the x, we put on the y, we have the result. And the same thing with -1, 0, 1 until 4. So when you see from the graph, we take t from this -2. T is here, the xy position is 8, -1, so 8 and -1 here. Okay. And then we will see that it has this direction. Okay. And this is the parametric curve of these two equations. Okay. Okay, this is if you want to sketch from each variable t. Okay, you can decide which t you are going to evaluate. Okay. And then we know that this is a parabola. This is a parabola. Okay. Parabola on the probably a y squared, right? Variation of y squared. Well, if you see from the equation, okay, we could take the equations and try to simplify. Okay, we could eliminate the t. Okay, if you want, this is one way to trace the curve. Okay, to visualize what curve will be. Okay. So the idea is we are going to eliminate the parameter. Okay, so this is also one method. One method to find what is the curve. Okay, so eliminate the parameter. So we know that t we can rewrite as y minus 1, okay? And then from x we can substitute this t, so y minus 1 squared minus 2 y minus 1. And if we try to solve this, so this will be y squared minus 4y plus 3. Or we could take this y minus 3 y minus 1. As you can see that y equal 1 and y equal 3 is the root, right? 1 and 3. Okay. So this method, the eliminate parameter, is one way to try to find what kind of curve the parametric equation has. Okay, while you write on this subject, let me just write the conclusions, just a simple conclusion from all of this. So x equal f of t. So this is curve with parametric equations. So you have y, you have x, and you have the range. Let's say the range is from A to B. So you have initial point, we call initial point, FA and GA, and terminal point at t equal b, of course. So this will be FB. Okay. Okay, that's the conclusions. Okay. Okay, next. Okay, next is this. So before this, let me write something first. So let's say we have x equal cosine t, y equals sine t, and we need to evaluate the t from 0 to 2 pi. Okay. So let's say we have at t equals 0, our x is 1, right? Our y is 0. So this will be 1, 0. And we could try to, for another t, in terms of angle or pi. So we can take maybe t equal pi over 2, x will be 0, and y will be 1. And we try for all the possible angle, the spatial value. And we could have this kind of curve. Okay. When we try t equals 0, this will be the point. We try t equal pi over 2, pi, 3 over 2 pi, and it will be a circle. Okay, it will be a circle. And if you remember how to rewrite the equations, how to exchange from rectangular to polar, from polar to rectangular, okay? One way to remember is we remember that the xy could be imagined as cos and sine. Okay? To be precise, we could imagine as, remember, x is r, okay? Which means in our case here, the radius is 1. We're going to see a lot this part, r cosine, r sine, later on in polar coordinates. This is actually polar, but not really polar, okay? Because we are still having x and y. It's not really converting to the polar axis. Okay? Now we could observe this, okay, this curve. Okay, if we take x squared plus y squared, this will be cos squared t plus sine squared t. And within these observations, we could take this as 1. Okay, so we could imagine that we are having the circle with radius 1. Okay, so circle with radius 1. And centered as in origin, centered in origin. Okay, now if we have the x is sine, 2t, and y is cosine 2t from 0 to 2 pi. Of course, it will be it will be a circle, but the difference is it has 2 instead of 1. So you can imagine, like for example, if you take pi over 2, it becomes pi, right? If you take 3 over 2, it becomes 3 pi. So what would happen is, if this is maybe this one circle, if we could imagine this part here, we could conclude that it will be we're circling around twice, right? We're circling around twice. So we could take this okay. So we could imagine that this will be the case. So when t is 0, the starting point is from here, and then we move on, and then we're going to see that it will reach this place 3 times. Okay, 3 times. So twice, circling twice. Circling twice. So the circle is still on the origin, right? Centered on origin. So there will be a case when the centered is outside of the origin. Like this one, let me maybe put up here to give you so this will be the circle for, let's say, x minus h plus y minus k equal r squared. And if r, or if x is r cosine theta and y is r sine theta, okay. And then this will be shifted. This is h units, this is k units. So the new, so this is original, this is shifted. This will be x equal h plus r, and this will be y k plus r. Let's move h unit. Maybe let me draw here. This is h. And this is k. So we could take the parametric as h plus r cosine t, for y is k plus r sine. This is for when the origin is changed, the center is changed, okay? Not in origin, but in other points, let's say H and K. Okay? I think this is something not to be memorized at all. Okay? This is just to be understood. Okay. Okay. What else? So this is still introductions, not yet calculus. This is the introduction for the parametric equations. Okay. Okay. I think we can go to here. Okay. Okay. This will be okay. So next is if we take x equals sine t and y is sine squared t. Okay. We would like to sketch this too. Now imagine that this will be equal to, if we eliminate the t, sine t is x. So this is another sine t here. So we could write and conclude that y is equal x squared. Okay. So this is pretty much just y equal x squared. So this will be the curve. From t equal -1 and t equal 1, and we're also going to see this oscillations from here and then going back and forward. Okay. Okay, I think we can have a break and we can continue on calculus part. Okay. Okay. Okay, we back again. Okay, so. Okay, I think we already solved this, and we can eliminate and see that it's just y equal x squared with the direction. Okay, now we move here a little bit here for just one note on this introduction of parametric. That is what we call the cycloid. Okay, if you remember, cycloid. This is the cycloid. So what is cycloid? Okay, we talked about cycloid before. Well, let us see what is cycloid. Okay, imagine you have a circle, this blue circle. The circle is rolling. Okay, it's rolling. And imagine maybe you put one dot on those circle. So this blue circle, put 1 point here. We call it P. Okay. And look on this point. When we roll, imagine that this is moving. When we roll, at every point when the circle changes the distance, the points also rolling, right? So it's rolling. And how the points change, how the points P change, and we connect all the possible changes, and we get this curve. This red curve. This red curve is what we call the cycloid. Okay? So the cycloid came from the change within the points in the circle when the circle is rolling. And then it will goes like all the time like this. And as for your reference, the cycloid, if you imagine, let's say you have A, B, okay? If you put something here and then it's going to be slide from A to B, some object, okay? And if you have any curve, okay? Let's say the curve is like this, or maybe another curve, okay? From all this tree, if your trajectory is a cycloid, the time it needs the object to be moved from A to B is the minimum. So if you have this cycloid trajectory, you will have a minimum time. Okay? So that's actually one case that, okay, if it's a cycloid trajectory, the times from point A to point B, it will be least, okay? It will be least time sliding, okay, for those objects. And now, if we see, okay, observe how we could break down the components on the cycloid. Okay. If we see here, okay, and we take that and make it bigger. Let's say we observe when P is here. When P is here, we break down P and taking this as a center of the circle, and we take a point we call Q. It has a radius R. It has an angle theta. Okay. We are going to break down the component, and we are going to find or define the x and y on this point P, the cycloid. So from this components, what we are going to first identify is this P. Okay, this is an arc of the circle, right? So the arc of the circle, if you know the radius and if you know the angle theta, what is the arc? Yes.
The angle or the radius?
The angle?
Or radius?
And per radius? Multiply or over? Multiply, right? Okay. Yeah. So the arc PT is equal to R theta. Okay. Everyone agree? Okay, agree? Still confused why R theta? This is because if you remember, the circumference of the circle is 2 pi r, right? Now we have this portion that is theta over 2 pi and multiply with this, so we have theta r. Okay, this is arc PT. Okay. Now this arc, imagine that the P is coming from here. Okay, this is the cycloid, part of cycloid. So P is moving from the origin, goes here, which means that this arc previously is touching this origin, right? Imagine that this is from here. So it goes here and it is going to rolling, right? Roll out this circle. Which means we can assume, we can make an assumption that this distance is the same distance that the arc PT rolled out. Okay? Agree? Okay. So assumptions first. So assume that the distance OT is equal to the arc PT, which is r theta. Okay, so that's why we have this distance r theta, same as the arc. Okay, now if we want to define this x, okay, from what we have r theta and we have this PQ. So x is r theta minus this PQ. And what is PQ? PQ, if we have this angle, then PQ, let me write here. Maybe it's too small, maybe here. Or maybe let me make the triangle. So this is theta, this is PQC, okay? This is R. So PQ is R sine, right? Yes, PQ over PC, okay. Right? So X is OT minus PQ, or R theta minus R sine, or R theta minus sine. And why? Why is this part here? This will be TC minus TQ. Oh, TC minus QC, sorry. QC. TC. Okay. TC is the radius, right? And QC, we get from here, is the cosine. Okay. So TC is R, and this will be cosine. Okay. Now the parametric on cycloid is x equal r theta minus sine theta, and y is r 1 minus cosine theta. Okay. And theta will be just a real number. Okay, that's the whole introductions for the parametric equations. Okay. We're going to move to the calculus part. Okay. Okay, everyone finished the notes or still right? Not yet? Okay. Let me wait for a couple minutes. Okay, now let's move to the calculus with parametric curves. Okay, now to start with, imagine we have x is a function of t, y is function of t as well. Okay. So from the chain rule, if y is differentiable, a differentiable function of x, which means y is f of x. Okay, if this is the case, then dy dx we can write in terms of the, or let me start with the dy over dt. Okay, let me start with dy over dt. So using the chain rule, we know that we can make this dy over dx and dx over dt. Okay. And we could define the dy over dt using the chain rule, as we remember from calculus 1. Okay. And if the dx over dt is not 0, okay, then we could rewrite the formula in terms of dy over dx is equal dy over dt over dx over dt. Okay. This is for the tangents, right? The tangents. But this is supposed to be dx over dt is not 0. If you maybe still visualize with a moving object in like in physics, so x and y is the distance, change in position, If you have dx over dt and dy over dt means that it will be the velocity. So dy over dx becomes the ratio between the velocity. So it's the slope of both of this. Okay? We could say that. So the slope of the tangent, we could also imagine as in physics. Okay, now to give you some insight, let me start with an example. Okay, so if we have x equal t squared minus 2t, it's the same example as previously graph curve. Okay, very early in the introductions. So the questions is find dy dx at t equal 4. Okay. Okay, you could do it with at least two methods. The first method is maybe if you would like to take the y equal 2 plus square root of x plus 1. Okay, this is one way, and then take the ddx, and you find that this will be equal to 1 over 2 squared x plus 1, and for t equal 4, x is equal to what? It's 16 minus 8, it's 8, right? So this will be 1 over 6, okay? One way. But you need to make this y in terms of x using the eliminations from this parameter, which is not really simple. This is quite simple, but for most cases it will be not simple. So let's try this instead of this. Okay, let's just try this. So dy over dx is equal dy over dt divide dx over dt. So we are going to derive each x and y with t. Okay. So dy over dt is just 1, and dx over dt is 2t minus 2. Okay. Remember, this is y, this is x. Okay. Sometimes students they mix up this, and this will be x, this is y. Oh. Okay. So sometimes this mistake happen. So this will be the result, and we are going to evaluate at t equal 4. Okay. So it's 8 minus 2, it's 1 over 6, okay? So it's the same result. Well, you could also just write this dy over dx as y prime t over x prime t. Okay, maybe it's more simple, less space to write, then probably better. So that's the first derivative, right? dy dx. Okay. Now the problem is when you have, or when you need to compute the second derivative. There will be a problem. If you are not understand the process, what's going on inside, you will get, or you will have some misunderstanding. Okay. So let me just go through, okay, and take the second derivative. Find the second derivative with the same questions, but now it's asking the second derivative. Second derivative, d squared y over dx. Now, if you're not careful, and then perhaps we start with the, let's say we have x is the same questions, okay? It's the same question. And we know that dy over dx from our calculation is 1 over 6 or 1 over, I just write just the equations first, okay? And then if you're not careful, you will write this, okay? So you imagine that dy dt is 0, dx dt is 2, okay? And then you write this will be equal to 1 over 2, or the 0 over 2, 0. Okay. Okay. Now this is something that expectedly to be happen, and this is wrong. Okay. This is wrong. Do you know why it's wrong? We start with the same method, right? Derive this, and this will be the result. Okay, here's why it's wrong. If it is just asking the first derivative, it's still okay. But when you do the second derivative, we need to remember, let me write here first. Let me make a cross here to note that this is not the way. Okay, and here it is if we start, okay. So notes. Okay, so when we did the second derivative, what's the definitions? Okay. The definitions is this the dx on dy over dx. Okay. So what you are going to do is you need to differentiate with respect to x on the first derivative. That's the second derivative. And then this d over dx, okay, this d over dx. If you could imagine the chain rule one more time, if you could imagine, this will turn out to be, this will be d dt, and this will be dx over dt. Now this is correct. So the way you solve the questions before is, let me write here, example. So we will write d dt of dy over dx. dy over dx is 1 over 2t minus 2. And dx over dt is 2t minus 2, right? Okay. And the derivative of this is 2t minus 2 squared. It's minus 2, right? And then divide by 2t. Or this will be minus 2 over, over 2t minus 2 cubed. And that's the result of the second derivative. So actually, what you need to remember, here, not two formula, just one formula, is the first one. Okay? The first one here, the tangent here. Okay? What you need to do is you change the y with dy dx. And if you need to find the third one, change that into the second one. If you want to find the fourth, change with the third one. Okay? So it's the same pattern, Okay? The same pattern, because we are having the y is actually a function of x, but y and x is a function of t. So that's why, if we are going to find the second derivative, if we do the same thing, like derive the y, derive the x, both sides, it will not suitable, or it's not fit with the definition. But the pattern itself is the definition of the derivative. So what you need to do is change this y. Change with dy over dx, change with the second derivative, third derivative. We need to find like the second, third, fourth, and so on. Okay? So change this y here. Okay. So that's why it becomes this. Okay. This is actually the same. If you imagine this becomes y, it's the same thing as the first derivative. Right? So if you change the y into here and become the second. Change to the second, this is the third. Okay. Oh, zoom out. How much? This? Or here, right? Like this, so it's going to be going down here. Right? Right. If this is 1 over something, then we can find something.
That is minus 2.
Derivative of this. Remember 1 over x? Derived is negative 1 over x squared. It's because of the x goes to -2 here, right? So negative. Yeah, take slowly. Mm-hmm.
Here you got dx squared. Why not?
The second derivative.
Why not?
It's just the way we write in the terms of t for the second derivative, it's like that. It's read as the second derivative, not as in the like a square. It's just the symbols. Okay. Now if you get confused, maybe just y double prime. That's also okay. Second derivative.
But you write y like this. Why you write x?
Yeah, how to say that? It's just like in mathematics. This is how you will write. Yeah, perhaps I will need to also, maybe if I find out why, I will help you. Okay. Okay, one example, and then I think we can finish. So one example. So let's say we have a C has equation x is t squared, y is t cubed minus 3t. It's actually the same as your example in your textbook. We are I think we will have more practice tomorrow. Okay, this is just to illustrate how we can solve. Okay. Number one is show C has two tangents at 3, 0 at that point, and find their equations. And then number two, find points on C where tangent is horizontal or vertical. Determine where C is concave, upward, or downward. I hope you still remember the terms. And the last one is sketch C. So first question on this parametric is we have this point 3, 0, right? We have this 3, 3, 0, which means that we we could take this 3, 0 into our x and we could get our t, right? We could get our t. So on those t, that will be our curve. So first thing is at 3, 0, okay, we could take this into our equations that t, it must be plus minus square root of 3. And then for this is for x equal 3, and for y equal 0, according to this point 3, 0, our y, which is, we can factor t out, this is equal 0, right? So the curve, okay, or the point, so the point 3, 0 arise when t is square root of 3 and t is negative square root of 3. Which means this positive negative, this indicates that the curve probably having crossed itself. Okay? So it's twice going to cross the 3, 0. Okay? So if we check the tangent, so check the tangent, this is 3t squared minus 3, and the other one is just 2t for the x over dt. So when t is square root of 3, then the tangent is, we could just take square root of 3 inside. It's 9 minus 3 is 6. 6 over 2 over square root of 3. This will be just equal to square root of 3. Okay. And then when t is negative square root of 3, dy dx is just the negative part. Okay. So these two results indicates that the slope, okay, it has a positive. So at the 3, 0, so let me illustrate what happens. So at 3, 0, let's say this is 3, 0. One curve of the tangent goes like that, and the other one is like that. So perhaps it will be having loop. It's having loop. Okay. Having a loop. And we could write the equations of the slope or the tangent. So equation of tangent, y equals square root of 3 x minus 3. We could just plug in the 3, 0 point. Okay. So at x, or maybe let me just write at 3, 0. Okay. And then the other one is this. The same, just the same. The difference is just the gradient. Okay. Okay, you can try the rest of the questions. For example, the tangent when it is vertical or horizontal. You could imagine when the slope is 0 and when the slope is infinite, right? When the slope is infinite, the concave upward, downwards, it means the second derivative, positive and negative, right? The second derivative greater 0 or less than 0, right? And then try to imagine how the sketch, how the sketch will be. We are going to discuss tomorrow, okay? But for now, we are going to, as usual, have a feedback. But you can write first for your notes. Okay. If you have maybe some discussion on, I think I give you exercise for chapter 8, just an introductory exercise. If you have some trouble, let me know which part. If we have time, we can discuss in class. Okay. I'm planning to I think finish the chapter 10 maybe next week. So this week, if we are in a good pace, I think tomorrow we can finish the all parametric and go to the introduction to polar. And for the polar, I think I need to give you some additional content to understand more how to graph a polar. Okay, because I want to just focus on the calculus part on polar. Okay, I think we could take the feedback as usual. I hope I'm adjusting the time. Okay. I think it's pretty similar like last week. The time, I mean. But this is for the surface area. Okay, surface area. Okay. I think. Okay, I think we can start with just asking your holidays. Your holiday fun, interesting? Well, if you don't want to answer, it's okay. Like if you haven't got inside Atomic Heart, working calculus free. Okay. Yeah, I also enjoy my holiday. Okay. Oh, you got sick? Okay. So sad. 100% no. Oh, okay. Yeah, we are going to have another holiday on April, right? So you can arrange another holiday. It is kind of awkward holiday in between the semester. You want to do something, but we still have the semester. Okay, let's start. Okay, let's start. Okay. Use your student ID, okay? So I can adjust easily. Okay, I think ready. Okay, start. I hope you can see in your screen, okay, in your screen. Carefully read the question. It's rotated about y-axis. The time limit around 8 minutes something. So maybe 2-3 minutes to understand the question. And then try to solve. If you are not confident, if you bring your calculator, you can use calculator for the integral part. But first, carefully write the correct formula. It's y-axis. means that it's going here, right? The radius is this. And then look up the equations. It's x. Okay, it's x. All it is x. So perhaps easier doing it in dx.
I have three.
Whoa. 11. Already submit. Okay, good.
Not good. Because
Maybe some of them quite good.
Something.
I know a few students just submit randomly.
Yeah, it's like
So,
Yeah, I think I give you an exercise. If you write your exercise, you try your exercise, you'll know the answer directly. Yeah, this is also checking your view, working on the exercise. No. Yeah, try to solve this. Sama-sama. So if you remember my tips, whenever you have a square root and solving the like arc length or surface area, sometimes you need to simplify. Simplify, which means that if it is in the quadratic equations, perhaps you can write in the quadratic form with the square. So you can cancel the square with the square root. Okay.
what's the real name? Are you sure? Oh, no, I rewrote it.
Normal line Yeah. Okay. Okay, who is 20? 20, okay. Randomly guess? Okay, your ID, and if you have any suggestions, you can write also. Okay, see you tomorrow. Okay, see you tomorrow.